Okay, so this is part 2 of Unit 5, where we're going to be dealing mostly with covalent type of bonds and structures, and we're going to look at how we're going to draw these. So first of all, it's very important to learn the rule for the octet rule that we're going to be using a lot, and so that's the normal, so to speak. And then we have, of course, we wouldn't want anything to be straightforward, a number of exceptions. So we're going to do these two together, and then we're going to look at resonance structures in the next lesson. And that's still going to be part of drawing Lewis structures, but I'm going to separate that into a little bit different lesson. All right, so Lewis, remember, he said that that in order to form a bond between two non-metals, that they each reach the status of a noble gas by sharing their electrons. And so before we get started on making the structure of a molecule, let's look at how you set up the electrons, okay? And we're going to use these little dots to represent an electron. Now, I want you to notice that the way this is set up, okay, is, for example, if you begin with lithium, we're thinking only about valence electrons. We don't care about the core or inner electrons in these cases. So we have lithium, we put 1 electron there. Our next one is beryllium. Well, beryllium has 2 electrons. For the Lewis structure, we're going to put 2 electrons on separate sides. It doesn't matter if you do them across from each other or next to each other, but they need to be on a separate side, okay? Boron, okay, that one has 3 valence electrons, and so we'll put 3 valence electrons here. Carbon has 4 valence electrons, so you'll put a dot on each side. When you get to nitrogen, now you begin to have paired electrons. And so you'll go all the way around, put 4 on each side, and then you'll add another one. Now, does it matter if your lone pair, the pair of electrons is up here or maybe down here? Makes no difference, okay, just so long as you've got them right. Oxygen has, Oxygen has 1, 2, 3, 4, 5, 6, for example. Okay, so you go along filling up like this, and the only thing you're interested in is the valence electrons. How do you know the valence electrons? The valence electrons is the same as the group number. Okay, so all you have to do is see if you're in group 1, 2, 7, whatever, and you will also have the valence electrons. All right, then we're going to take our formula that we're given, okay, and we're going to determine, first of all, what the least electronegative atom is, because that's we're going to put in the center. We're going to count valence electrons, okay, so we're going to count up all of the valence electrons in the entire structure. We're going to draw bonds, okay, and for each bond we're going to take away 2 electrons, okay, and so that's going to help us figure out what to do. We're going to add to the outer electrons 8 electrons, okay, to make it a full noble gas configuration, and then anything left over we're going to deal with on the central atom. Okay, so I just put this in here to tell you if you don't have enough bonding electrons, okay, to make an octet, it's very important to always make sure you're making an octet. You can do these 3 strategies. You can use multiple bonds, meaning double or triple, rather than just a single. We can violate the octet rule under certain circumstances, which we'll look at later, and we can possibly make ring structures, okay, in order to make the structure valid under the Lewis dot theory. Now, there's a couple of things you want to keep in mind. Remember, hydrogen can only make one bond. It only has the one electron to share. Okay, carbon, most of the time, is going to have 4 bonds. Okay, one thing I know is carbon isn't going to violate our octet rule. Carbon never violates the octet rule. For now, okay, don't double bond your halogens out of group 7. All right, now we will be doing some stuff that has some double bonded later, but while we're learning how, remember our halogens, for example, chlorine, it's going to have a Lewis dot structure like this with just one electron that it can share. These atomic orbitals are filled, okay, so we can only get one bond on our halogens. We'll look at this more later. With only one exception, well, actually, no, I'm getting ahead of myself. For multiple bonds, these 5 elements can undergo multiple bonds, okay? So they can participate in carbon, double bonds, nitrogen, oxygen, sulfur, phosphorus. All of those can have more than one bond. Now, we're going to be looking at some other things later. And so if our central atom ends up with an octet, okay, we're going to end up having to be in period 3. Again, this is going to be later when we look at the exceptions, but I just wanted to kind of put all these rules up front. All right, so let's look at the configuration of water. All right, water. We've got 2 hydrogens, so we have a hydrogen here, and we'll put another hydrogen over here with its 1 electron. When we fill in oxygen with its Lewis dots, it's got, oops, let me do it this way. It's going to be 1, 2, 3, 4, okay, and 5, and I'm going to put this one down here, 6. Okay, so this was a 1s1. This is valence electrons. We have 2s2, 2p4 for a total of 6 electrons. Okay. Now, when they bond, these 2 will bond together, and these 2 will bond together. And so you end up with a structure that looks like this. Okay. And just as a reminder, the electron density is going to be pulled in this direction, okay, because oxygen is more electronegative than hydrogen. And so this is polar. These are polar bonds. But at any rate, they overlap. Remember, we've got overlapping, so let me put in this P. Well, I'm just going to make this our oxygen, okay? Here's hydrogen. It overlaps here. Hydrogen overlapping, okay? So they overlap in order to have those 2 electrons form that localized bond that we're talking about. So I want to do some examples. So I'm going to spend most of our time drawing over the next few days, and I know I'm not the greatest, artist. I hope you will forgive my artistic abilities. But let's start with carbon tetrachloride. Carbon tetrachloride. 1 carbon, 4 chlorides, and that they're at the end, so we call it a chloride. Let's count up our valence electrons. There's 4 for carbon, which is in group 4, and then we have 4 for the chlorine at 7 each, and so this works out to be equal to 32 electrons. Okay, so we've got to place 32 electrons on our carbon tetrachloride. Now, the first rule is the least electronegative atom is the central atom. Now, most of the time, this won't be a problem for you because for most things, the central atom is almost always going to be the first one. Okay, so you don't have to usually think about this too much, but it is a rule. So we're going to put the central atom as carbon, and then we're going to draw bonds between the outer atoms and the central atom. So in this case, we're going to put chlorine, 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 and chlorine because we have to make 4 bonds. Then all outer atoms get an octet first after you get this on here. Get the octet. And so, see if I can be neat about this. I'm going to put an octet of electrons around the chlorine. Now, what about this? So far I have 6. What about this bond? Remember, this bond is shared. Okay, so this has 8 electrons around it. So I'll put around these, and if the machine, if the board looks like it's jumping, it's because it is. So all of my outer electrons now have an octet because this counts as 2 electrons for the carbon and the chlorine. Okay, both of them get to count those 2 electrons as their own. So fill out all the outer atoms to give them an octet. And in this case, and then you count up your valence electrons. So let's count and see how many we have. We have 2, 4, 6, 8. Each bond counts for 2. 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. That's 32 electrons on this. We were supposed to get 32 electrons. So sometimes it helps to make yourself a little note. Remaining electrons in this case is equal to 0. Okay, so we now need to check. Okay, in this structure, let me just put, well, no. Not only do we have to have all the outer electrons with the octet, like this one was, but the central atom, let's give me a different color, the central atom also has to have an octet. So I'm going to count around in a different color, I guess, the bonds. Each bond is 2 electrons, so this one has 2, 4, 6, 8, and so carbon has an octet. I'm real happy. This is a great structure, just like it is. So let me redraw that without all that stuff on it. This is a valid Lewis dot structure that fulfills all the rules. I used all the electrons, everything has an octet, and so I'm a happy camper with this. Now let's move on to, different picture. Let's do something like P, I'm really sick of green, pH4. This is going to be an ion with a positive charge. Now the reason I'm doing this is for 2 reasons, but one of them is because I want you to know how to count your valence electrons. Okay, so valence electrons are going to be equal to whatever the period group number, the group number is, all those sum together, minus the charge, minus whatever the ion charge is. All right, so we've got P, okay, but that's in period 5, group 5, so that's 5. And we've got 4 hydrogens each from group 1, so that's 4 times 1. And then I have this this positive charge. Let me do this. We have 9 electrons so far, and we're going to subtract that positive 1 charge to give us 8 electrons. Okay, so subtract the charge. Really critical. Don't add it. Don't change anything about the charge. Just subtract whatever it is. So we need to put 8 electrons around our pH4 structure. So P is going to be the central atom. H, 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 and H. Now, can I put outer electrons on, can I put electrons on the hydrogen as the outer atom? No. Hydrogen forms one bond, remember, because it only has one electron. So there's no octet I can put around these hydrogens out here. Okay. So I count, like I'm going to count the octet first around the phosphorus. So here's 2, 4, 6, 8. Excellent. That's got an octet. And even though I can't put an octet around the hydrogen, it's okay because each hydrogen has 2 electrons, which is something we call the duet rule, because a hydrogen can only have those 2 electrons. So that's a good structure. And one more thing, this is an ion. Okay, so you will often see those in these big square brackets and with a charge outside to indicate that it's an ion. This is a good structure. We like it. It's perfect. Fulfills all of the rules of Lewis dot structures. Oh, why do I keep doing that? All right, next let's look at a molecule called cyanic acid, HCN. All right, so we're going to count the valence electrons. That'll be 1 from the hydrogen, plus 4 from the carbon, plus 5 from the nitrogen. So we're going to have 10 valence electrons. Okay. Also, now I told you that usually the first atom is going to be the one that's going to be your central atom. But can hydrogen ever be the first atom? The central atom, and the answer is no. Okay. In this case, the least electronegative atom in this case is carbon. So even though there's a hydrogen up here, which is the way some formulas are written, hydrogen's never going to be a central atom. It can only have one bond. And so carbon is going to end up being our central atom in this case. So we're going to put in the bonds to the outer electrons. Okay, outer atoms. And then we're going to fill in the outer bonds. Okay, so 2, 4, 6. Now, let's see. I've used 2, 4, 6, 8, and 10. I have 10 electrons. Oops, I've got these in the wrong color. I have 10 electrons. Still in the wrong color. 10 electrons. Excellent. I'm very happy. Looky here, I had 10 valence electrons, and I filled in 10 electrons. And so I'm in good, right? And the answer is no. Look, I have an octet around the nitrogen, 2, 4, 6, 8, but what's going on with the carbon? Carbon does not have an octet. Okay, so I am not in good shape yet. And I can't just add some more. I can't just put on some more electrons because that gives me 14 electrons to make that full octet, and I don't have but 10. Okay, so I'm going to have to rethink this for a minute. I don't have enough electrons to make this structure obey the octet rule, at least not on its surface. But look, I can make a carbon and nitrogen double or triple bond. That's one of the things I can do. So let me move this pair of electrons over here, okay, and then we're going to have HC double bonded in, and we still have a set of electrons here. We count 2, 4, 6. There's 4 electrons here because of the 2 bonds. 2, 4, 6, 8, and 10, so that's good. Again, I've got 10 electrons, but how many electrons do I have around carbon? Well, I only have 6 electrons around carbon right now. 6 around carbon. Okay, so that's not an octet yet either. So I'm going to do one more shift and put this over here and see if I can make this into a good octet. Make one double bond. I'll have one pair of electrons left on the nitrogen. Now, I'm going to count 2, 4, 6, 8, 10. Good, finally, I'm there. Let's look at our nitrogen. Put this back up so you can see it. Does nitrogen have an octet? It gets to count all of the bonds and that lone pair out there. So that's 2, 4, 6, 8. I think I didn't tell you about lone pairs. I better do that. 2, 4, 6, 8 gives me an octet there. And carbon gets to count the bonds between the nitrogen and the hydrogen. So now I've got 2, 4, 6, 8 on the carbon. What about hydrogen? I don't have an octet around that. Is that okay? Yes, because hydrogen can only have 2 electrons maximum, so that's a good structure. So let me point out what happened. We didn't have not enough electrons to make octets. So in this case, I made multiple bonds in order to give everything an octet. And this is a good Lewis dot structure. And we will be looking at this again. And we're going to actually be looking at several of the things I'm drawing today again later. Now, I meant to put this into this PowerPoint, but I guess I didn't. So, stop. I just want a blank page. And finally, I want to talk about the carbonate ion for a minute. Okay, carbonate. CO3 2-. So it's got 4 valence electrons plus 3 times 6 for the oxygen, because that's in group 6, minus the -2. Okay, this works out to be equal to a total of 24 valence electrons. I'm going to put carbon in the middle. Okay, I'm going to add the oxygens as bonds, and then I'm going to fill out the octet around every outer atom. All right, now another way you can count this, which is what I typically do, is I know that this group here is 8 electrons, because that's going to fulfill my octet. So I count 1, 2, 3 bonds. 3 times 8 is equal to 24. And so I've used up all my valence electrons. Excellent. I'm set to go, right? Well, let's look at carbon. Carbon has 2, 4, 6 valence electrons around it. Is that an octet? No, we're violating the octet rule. Okay, so this is wrong. Something's wrong here because carbon doesn't form an octet. So what I'm going to do, here is I'm going to pull one of these sets of octets, electrons off of the carbon or off of the oxygen, and I'm going to form something that looks like this. Looks like this. Now, we already know these two fulfill their octet, so we're not going to deal with those. But what about carbon? Well, carbon now has 8 valence electrons in those bonds, so it has 8 valence electrons. That one's good. And what about this oxygen? It has this pair, 2, 4, and then these right here. So oxygen also has 8 valence electrons. And so I've reached an octet by making a double bonded carbon oxygen. I'm not going to put those electrons out there, but that's how this is going. I will put it on this oxygen so you can see. It looks like this. That is a valid Lewis dot structure. The point here is, before you start thinking about any exceptions, which we haven't done yet, you've got to make sure that you actually have an octet around everything before you start dealing with other potential problems later. Now, let's see. Seems like I have a couple more I want to talk about here. What about a structure like SOCl2? Well, sulfur is in period 6, so I've got 6 from sulfur, valence electrons. I have 6 from oxygen, also in period 6, and I have 2 times 7 for the chloride in period 7. And that works out to be equal to, I don't know, I didn't add it up. 12 and 14 is 26 electrons. Sulfur is going to end up being your central atom here. I'm going to add the oxygen, the chlorine, and the chlorine. Okay. Then I'm going to put our central, I'm going to fill our outer atoms with an octet. And then I'm going to count, okay? How many electrons have I used so far? Well, now remember, each one of these bonds has an octet, and I have 3. So 3 times 8 is 24 electrons. But I have 26. 26 electrons minus 24 electrons means I have 2 electrons that I need to put on this structure somewhere. So I already know that sulfur, oxygen, chlorine and oxygen are all octets. I'm going to put the remainder of these 2 electrons out here on sulfur, like so. Now, let's check and see. I've now used up 26 electrons, so now I have 0 electrons left over. Let's see if we fulfill our octet rule. Well, we know these outer electrons, the chlorine and the oxygen, were fine. What about sulfur? Sulfur has the 6 electrons in these bonds plus this 2. So, oops. So sulfur has 6 plus the 2 in the lone pair, and that gives you 8 electrons, so this is a good structure. Okay, this is a good structure. Let me redraw it one more time. So what I'm saying here, oops, that got way off balance, but what I'm saying here is if you have extra electrons, more electrons, always put them on the central atom. All right, and in this case, by doing that, that also allowed us to fulfill the octet rule on the sulfur. I do want to talk for just a second about bonding and non-bonding pairs since I'm here. And I didn't do this earlier. So let's talk for just a minute about non-bonding and bonding pairs. Okay, so I still wish I'm still going to redraw this. All right. Well, as I'm sure you can imagine, oops, better put those guys on there. A bonding pair are the two electrons shared in a bond. Two electrons that are shared. Then the non-bonding pair is also called lone pair, just because we wouldn't want to have just one rule. And I'll usually call them lone pairs, but these are, each and every one of these separate sets of electrons are lone pairs or non-bonding pairs. In other words, they have to go with the atom, but they don't bond to anything else. All right, so I really wish you would do several of these problems, but until you know how to do the exceptions, then you're going to run into things that don't make a lot of sense. So let's go ahead and talk about the exceptions to the rules. And so there's, even though everything should always do its very best to make an octet, okay, there are times when it just isn't going to happen. And there's three exceptions. Okay, electron deficient structures, okay, radicals or odd numbers of electrons, and expanded valence shell structures. Okay, so those are three possible exceptions to the octet rule. So let's start with the two most common exceptions under the electron deficient groups. Okay, now beryllium. Let's talk about where beryllium is. Let's look at our periodic table. Here's this is period 2. Lithium, beryllium, boron. All right, lithium, beryllium, and boron. Now, if we put something with lithium, that's a non-metal, it's going to be ionic. In other words, the lithium is going to lose its electron to whatever the non-metal is under most circumstances. However, beryllium and boron are exceptions. Beryllium, again, you would assume it's ionic because it's in the metals in period 2 and group 2, and the boron is also an exception, but that's a little bit different. Okay, but beryllium is not ionic. Remember, I told you on that electronegativity scale, period 2 is very high in electronegativity. And also, there's this range of possible polarity or non-polarity. It just so happens that beryllium ends up making more of a covalent bond than an ionic bond. But beryllium, remember, has a Lewis structure, just Lewis dot structure all by itself with just 2 electrons. So it can only form, the only thing it can do is form another bond, okay, here, like so. And so beryllium chloride, even though it's even though beryllium is a metal, it's high in period 2, it has high electronegativity, and it ends up acting covalent. All right, so beryllium can only have 2 possible bonds. Now, if you look down to the next one, magnesium, I think, that becomes ionic, and so that's not going to really have the same characteristics as the beryllium. Excuse me. Now, boron. Okay, boron is another exception. That's still in period 2. Let's draw its Lewis dot structure with just its, for just the boron. Notice that, again, it doesn't have enough electrons to make 4 bonds. It can only form a bond with these overlapping, for example, hydrogens. We could put hydrogen in here. We could put chlorine in here like this one is. Oh, I see I covered up the lone pair there. Anyway, boron is another exception. It's more covalent than non-covalent, but it only has enough electrons to make 3 bonds. Okay, so those are electron deficient possibilities, exceptions. Then there's the exceptions to the octet rule, okay, under this possible thing called odd number electrons. If you count an odd number of electrons when you're doing your valence electron count, recount. It's very rare to have a radical, but it does happen, okay? So we're going to look at a structure called, I hope you can name this, but I will for you, nitrogen dioxide. Meaning I have a nitrogen and 2 oxygens. And this has 5 plus 2 times 6, okay, valence electrons. This works out to be an odd number, 17. You should recount, and you should make sure, but in this case it's true. Also, I want you to notice that we have an ion that we deal with that has a negative charge on it, and so that's going to be different from the nitrite ion, because the ion has the charge on it. So that wouldn't have a odd number. Whoops. All right, so let's put together this structure of nitrogen dioxide. So nitrogen is the least electronegative atom. It's going to be the one in the center. And so I'll put the nitrogen in the center. Then I'm going to fill the octet on each of these outer electrons. And then I'm going to count. I have 8. 2 times, so that's going to give me 16 electrons that I have used. All right, so now I'm going to put this extra electron on the central atom. So the radical goes on the central atom. So now I have 17 electrons. Okay, now, question, is this a good structure? No. First of all, it's not a good structure. It's not a good structure because the nitrogen is violating the octet rule. And remember, I told you the carbon, nitrogen, oxygen, and fluorine always follow the octet rule, except for this one chance. But right now, nitrogen has 2 from the bonds, 4. It has only 5 electrons around it. It's not even close to the octet rule. So I need to rearrange this to get it at least to where I've got as close to an octet as I can get. And so in this case, I'm going to make a double bond here. That'll leave me with 2 sets of lone pairs. I'll make this an octet still. And now I'm going to count, oh, and my radical electron goes on that central atom. And so this has 8 electrons, and this bond has 8 electrons. And now what about the nitrogen? Nitrogen gets to count all of this. So nitrogen has 6 from the bonds, so 6 electrons from the bond, plus the 1 radical electron. And so even though nitrogen doesn't quite get the octet rule, it's the only exception for carbon, nitrogen, oxygen that you're going to see is that they can have a little bit less, okay, by putting just the radical electron on that central atom. So it doesn't fulfill the octet rule because there just isn't enough, there just aren't enough atoms. Now, could I have done a structure like this where I put in a triple bond, okay, and now I'm going to have this radical on here. Now let's look at what happens to nitrogen here. In this case, nitrogen is what I'm thinking about. nitrogen has 8 electrons from the bonds plus the 1 electron from the radical, and that gives you 9 electrons. Nitrogen is never, never, ever going to have more than 8 electrons. Okay, so this is not a valid structure because the things in period 2 don't get to have more than 8 electrons, no matter what. Okay, they typically will have 8 electrons if it's carbon, nitrogen, oxygen, and fluorine. They're going to have 8 electrons. The only exception is if it's an odd number. Okay, and if it's an odd number, it will have one less than an octet somehow. So each of these would have 7 electrons on them. All right, then there are one more exception to the octet rule, and those are called, I didn't mean to get that so big, but expanded shell exceptions. Okay, in expanded shell exceptions, that means that the central atom has more than 8 electrons. On it, and it's around it. Okay, and there are 2 forms of this. Now we'll look at these a little more carefully when we start thinking about geometry some, but this is a trigonal bipyramid, and it has 5 bonds. 1, 2, 3, 4, 5 areas there. Okay, and so phosphorus has 10 valence electron, or 10 electrons on it, which is obviously not 8, but because there's d orbitals. Okay, this can happen because now after period 3 and beyond, you can use d orbitals, so you can expand into other shells, and so that allows you to have phosphorus with 10 valence electrons around it. And then for sulfur, in this case, SCl with 5 Fs. This is an octahedral. An octahedral has its kind of problems, but there's 1, 2, 3, 4, 5, 6 bonds, or 6 areas of density. And so this also, around that central atom, I mean. And so this also is going to be a violation of the octet rule, where you can only have 4 areas of density around it. Okay, so again, that's because sulfur is in period 3 or more. Okay, so it can expand into its d orbitals. All right, so let's do a couple of examples. A couple of more drawing examples anyway. All right, so let's do the structure PCl3. Okay, so this is going to have 5 from the phosphorus valence electrons plus 3 times 7 for the chlorine, or 26 electrons. Phosphorus is going to go in the center. Add all the electrons to the outer electrons. Okay, and then I have 8 in this one. So 8 times 3 means I have used 24 electrons. I have 26, and so I have to put 2 electrons on the central atom. 2 electrons on my central atom, like so, and then I recount. I have 24 electrons now, and 26 electrons, and the chlorines all will fulfill the octet rule. The phosphorus fulfills the octet rule as well. It's got 6 electrons in the bonds, and then this lone pair of electrons, that gives us 6. what about something like aluminum chloride, AlCl3? So aluminum is in group 3, and then there's 3 from group 7. That again gives us 24 electrons. We'll put aluminum in the center and the chlorines out here. Add their valence electrons there. And now I've got 8 in this bond, so 8 times 3 is 24. But this time, I've already used all of them. Is there something wrong with this? Well, aluminum has 6 electrons. It doesn't fulfill the octet rule, right? Because there's the 3 bonds with 2 electrons each. And now aluminum's got a problem here. Or does it? And the answer is no, it doesn't. Let me show you why. Because aluminum is in period 3, and it has 3 places where it can form a bond. And so this is an electron deficient structure, but it's perfectly fine in this form, aluminum and chloride. 3 bonds and nothing else. Let's see. How about IF4 plus? Okay, so I have 7 valence electrons from the iodine, plus 4 times 7 for the fluorine, minus that positive 1 charge. Remember, we always subtract a charge. That gives us 34 electrons. And iodine, we know the most electronegative atom is fluorine, so it's never going to be a central atom. Put on our F's here and fill in the octet around the outer atoms. And then we're going to count. Okay, now, we know this is going to be 8. 8 times 4 is 32. I go back up here, I still have some electrons left over. 2 electrons. But iodine, look, iodine has an octet. Okay, 2, 4, 6, 8 from the bonds with the fluorine. So what am I going to do? Well, the answer is always, remember, always put that lone pair of electrons on the central atom. But now that means I'm breaking our rule that says everything has to have an octet. I'm not going to put on all these atoms for a minute, the electrons for a minute. I just want to show this. Okay, so there's a lone pair of electrons on that central atom, which means now I have 10 electrons, not 8. But is this okay? And the answer is, well, iodine is in period 3 or more, and so I can break this, and this is an expanded shell electron exception. Now, you cannot take shortcuts when you're doing Lewis dot structures, especially when you first begin. You have to keep working on it and keep working on it. Now this, since it had, we'll look at this more carefully later. Oops, better include that F. Now this is the exception for the trigonal bipyramid. It has 5 possible electrons around it, 5 areas of density. And so that's a trigonal bipyramid exception. Let's look at an octahedral exception. Let's look at TeF5 minus. Okay, so tellurium is in period 6, plus 5 times the halogen, period 7, and then I'm going to subtract -1. Subtract -1, and this is going to give me 42 electrons that I need to deal with. And already you can see that this is going to have to break the octet rule because I have 5 fluorines attached. And I'll put them like so. Okay. Then you're going to fill your outer octet, your outer atoms with the octet. Okay, so I know each one of these is an octet. So 5 times 8 gives me 40 electrons. I have something left over, 2 electrons left over. Where do they go? They go on the central atom. Okay, and so now I can see that I have 6 areas of density that I need to deal with. And we'll look at this more, but that's one of the octahedral expanded shell exceptions. All right. Let's try this one. I want you to draw this for a minute. How about H2CO? Okay, and remember, hydrogen can never be a central atom. We'll make carbon your central atom. So let me help you out. For your valence numbers for now, that's 2 times 1 plus 4 plus 6. And so we're going to have 12 electrons. Okay, so I want you to draw that. I'll give you 30 seconds. All right, so you should have come up with a structure that looks something like this initially. You'll put your you'll make the octet on your outer oxygen. Can you make an octet on the hydrogen? And the answer is no, it can only have the one bond. And so let's count. 2, 4, 6, 8, 10, 12. 12 electrons. Is it okay if it's not got an octet? Is it okay if it doesn't have the octet? Remember, because this would only have 3 bonds or 6 electrons. All right, can we do that with this? No. No, no, no. First of all, this violates the octet rule, and you can't use one of your exceptions here. Carbon is going to not violate the octet rule. So that means I need to bring down a pair of those electrons and share those between the carbon and the oxygen. And so it's going to look like that. Now do I have an octet around everything? Well, the hydrogens only have 2, of course. This guy, this oxygen, he's got 2, 4, 6, 8 valence electrons. The carbon has 2, 4, 6, 8 valence electrons on that carbon, and I can't use one of the exceptions to break this kind of a rule. Okay, so you've got to be careful about what you can and cannot do. Your first job always is to try to make an octet out of your molecule. Only when you can see that there's no possible way to do it do you then begin to allow yourself to do one of these exceptions. Now, I'm really not done with this. We need to talk about resonance structures. They're a big part of learning how to draw Lewis structures and understanding the chemistry of some things, but we'll do that in the next lesson. if I can